In this video, we're going to talk about complex numbers and what happens when we solve a quadratic equation where the solution is a complex number. So what is a complex number? Before we can talk about that, we should probably talk about the different number systems that we are familiar with. So we'll start small and get bigger. So the first number system is the natural numbers. And the natural numbers consist of, sometimes they're called the counting numbers. So they start at 1, 2, 3, 4, and they continue on. Branching out from the natural numbers, we have whole numbers. And whole numbers are very similar to natural numbers, except they begin at 0. 1, 2, 3, 4, etc. So natural numbers are counting numbers. We call them counting numbers because when you're counting, you don't start at 0. We always start at 1. So whole numbers are an expansion of the natural numbers by 1. Next up, we have integers, which comprise of positive and negative whole numbers. So all the negative whole numbers, 0, and then the positive whole numbers. Sometimes I can write 2, 3, and so on. So we go in both directions there. Next up, we have what are called rational numbers. And rational numbers, if you look at the root of the word rational, we have ratio. So a rational number is any number that can be written as a ratio or a fraction. A precise definition looks like this. We would say a rational number is any number that can be written as a fraction a over b, where both a and b are integers. So some examples of rational numbers, something like, 2/3, -5/4, 6 is a rational number because we could write that as 6 over 1. So any number we can write as a fraction is a rational number. Next up, we have irrational numbers, and irrational numbers are kind of the converse of rational numbers. They're numbers that cannot be written as fractions. So these are numbers that cannot be written as fractions. And we'll use the definition before, so they cannot be written as a over b, where a and b are integers. So some examples of irrational numbers, well, square root 2 is an example of an irrational number. Pi is an example of an irrational number. Square root 2 is 1.41, etc., etc. Pi is 3.1415, etc., etc. The exponential constant e, that's an example of an irrational number. So each of these values are not, we say they're non-repeating, non-terminating decimals. Terminating. And what that means is their decimal approximation continues forever. It never repeats. It never terminates. So an example of a repeating decimal would be, this is decimal. An example of a repeating decimal would be something like 1/3, because that's 0.3333, etc. That's an example of a repeating. I really had a hard time writing this. This is, I need a G in here. Non-repeating, non-terminating. Okay, so 1/3, that is repeating. It doesn't terminate, though, because it just continues forever. So that's a little bit about irrational numbers. So all of these sets of numbers are comprised of what's called, or comprise what's called, the real numbers. Okay, so the real numbers are made up of natural, whole, integers, rational, and irrational. Now there's quite a lot of overlap in these sets, and that's okay. But one way we can think about real numbers is any number that has a location on a number line is called a real number. So, you know, the numbers we've talked about so far, well, what do we have? We had 2/3. So if 1 is here, 2/3 is right here. That has a location on the number line. Pi, which is a little bit more than 3. Pi is about right here. That has a spot on the number line. -10 has a spot on the number line, and so on. 1/3. Square root of 2, which is 1.14 or 1.41 about. Okay, so all of these values make up the real numbers. So when we talk about real number solutions or find the domain in the real number set, this is what we're talking about. We're talking about any number that's on the number line. Now, this is one type of or set of numbers, the real numbers. The flip side of this are the numbers that are not on the number line, and these numbers are called complex numbers. So the complex numbers, we can think of those, well, again, as numbers that are not on the real number line. And so we can think of these visually if we have the real numbers along the horizontal axis, and then the complex numbers. Well, complex numbers sometimes are called imaginary numbers. And so we would have the imaginary numbers on the vertical axis here. What is an imaginary number? So if we take the square root of -1, we define that as being the number I. And then if we square both sides, we have -1 is equal to I squared. So these two equations give us the definition of an imaginary number. So I'll just rewrite that. Square root -1 equals I. So what a complex number is, a complex number is a number that is made up of a real part plus an imaginary part. Okay, so how we will typically write the standard form of a complex number is A plus BI. So the real part is this first term, the imaginary part is this second term. And A plus BI, where A and B are real numbers. So this is our general form. So back up to this graph, let's look at a couple of complex numbers. If we have 3 plus 2i, well, that's going to be 3 along the real number line, positive 2 along the imaginary number line. So there's that point. How about -4 plus I? Well, that's going to be -4 on the real line and +1 on the imaginary line, so -4 plus I. Similarly, if we just have, 6, that's going to be just 6 along the real number line. So that's the same thing as 6 plus 0i. And then we could also have a complex number that just has an imaginary part. So how about -2i? It's going to be down here. Let me label these -2i, and this one was 6. So -2i, that's going to be 0 plus, or rather 0 minus 2i. So if we want to write any of these complex numbers in that a plus bi form, even if it only has either a real part or an imaginary part, we can still write that as a complex number. So working with complex numbers, when we add, subtract, multiply, and divide them, they follow very similar rules as with any time we are adding, subtracting, multiplying, and dividing regular binomials. So adding and subtracting complex numbers. Let's just look at this through a series of examples. If we have 3 plus 4i and we add that to 6 minus 2i, so two complex numbers here. If we remove the parentheses, add the like parts, so we have 3 plus 6 is 9, 4i minus 2i is plus 2i. So about what we would expect there. If we have 4 plus 6i minus negative 3 minus I, well, remove the parentheses. 4 plus 6i minus negative 3 is going to be plus 3, minus negative I is going to be plus I. So combine the like parts, we'll have 7 plus 7i. So again, adding and subtracting about what we would expect. If we are multiplying, 3 plus 4i, let's multiply that by 6 minus 2i. So same complex numbers as above, but now let's multiply. So when we multiply, this is just as though we were multiplying two binomials, so we're going to distribute this out. 3 times 6 is 18, 3 times negative 2i is negative 6i, 4i plus 6 is positive 24i, and then 4i minus 2i is negative 8i. Now, the like terms here are the negative 6i and 2i. Oops, forgot to write that as negative 8i squared. And then I squared, remember, I squared is equal to negative 1. And that's because negative 1 square root is equal to I. So this is kind of our guiding definition for the imaginary part. So I squared, we're going to rewrite that as negative 1. So what we're going to have is 18, minus 4i, and then negative 8 times negative 1 is going to be plus 8. So we'll ultimately end up with 26 minus 4i in a plus bi form. So multiplying two complex numbers, just like multiplying two binomials, the one thing we need to be careful of is if we end up with an I squared, we need to convert that into negative 1. And then lastly, if we are dividing, suppose we had 3 plus 4i, I guess that's my favorite complex number, and let's divide by 2 minus 5i. Okay, now this is much like if we had a radical in the denominator. What we would do is multiply by the conjugate. So the conjugate of the denominator is going to be 2 plus 5i. So we multiply the top and bottom by that, and then distribute out the numerator, distribute the denominator, and then we can simplify. So we'll end up with 6 plus 15i plus 8i plus 20i squared. In the denominator, we'll have 4 plus 10i minus 10i, and then minus 25i squared. So in the numerator, well, we have 15i and 8i, and then we have this I squared here. See if I can squeeze it in. So I squared is going to be negative 1. So what we get is 15i plus 8i is 23i, and then 6 plus 20 times negative 1. So that's 6 minus 20, which will be negative 14. So negative 14 plus 23i divided by, well, in the denominator, the whole reason we multiply by the conjugate is so that we can cancel out the I terms. So 10i, negative 10i, that goes away, and then I squared here, we have negative 1, so 4 minus 25 times negative 1, so that'll be 4 plus 25, which is 29. So we end up with 29 in the denominator. So this is an appropriate way to write this solution. Or if we want to totally write this in a plus bi form, what we'd say is negative 14 over 29 plus 23 over 29i. So just explicitly writing this as a plus bi. Okay, so that's about all that we're going to do with the algebra of complex numbers. And then the whole reason, or one of the main reasons we work with complex numbers and imaginary numbers is so that we can solve quadratics that end up with solutions that have imaginary parts. Let's check out this example. X squared plus 9 equals 0. Now this is a this is a quadratic equation because we have an exponent. The highest exponent is 2. So to solve this, we could use the quadratic formula. However, if we solve for x squared, we get something that looks very close to being two perfect squares equal to each other. So let's take the square root here. What we're going to end up with is x equals plus or minus the square root of negative 9. Well, when we have square root of negative 9, we can think of that as the square root of negative 1 times 9. And when we do so, well, there's two parts. We have the 9. Well, the square root of 9 is 3. And the square root of negative 1 is I. So the square root of negative 9 is going to be plus or minus 3i here. So plus or minus 3i will be our solution. And then let's look at a second example. Let's say x squared plus 2x plus 2 equals 0. Now to solve this, this is a quadratic, it's set equal to 0. Let's try to factor, well, x and x, and then what multiplies to 2? Well, that has to be 2 and 1 in some order. Well, if we do that, we're not going to get a middle term of 2. So this is not going to work here. So we could try and use the quadratic formula. We could try to factor, or I'm sorry, complete the square. I'm going to use the quadratic formula here. The a value is 1, b value is 2, c value is 2. So we're going to have x equals opposite of b plus or minus square root b squared minus 4ac all over 2 times a. Negative 2 plus or minus, we'll get 4 minus 4 times 1 times 2 is 8, so 4 minus 8 divided by 2, and we end up with negative 2 plus or minus square root negative 4 over 2. So we need to take care of that radical. Well, square root of 4 is 2. Square root of negative 4 is going to be 2i. If we want to think of this like negative 1 times 4. So the negative 1 comes out as I, and the 4 comes out as 2. So we'll write that as 2i. So we end up at negative 2 plus or minus 2i all over 2, and that's what x is equal to. And then if we can simplify this a little bit. If I factor out a 2 from the numerator, we get negative 1 plus or minus I divided by 2. The 2's cancel. So ultimately we have x equals negative 1 plus or minus I. So we get two complex numbers, both in the form a plus bi.